welcome back. In this video, we talk about ensemble methods. Ensemble techniques combine weak learners either sequentially or in parallel. The sequential approach involves using weak learners one after the other, each time more heavily weighting the mislabeled observations as they are input into the next learner. The parallel approach uses many weak learners that are created at the same time and aggregates the results. An example of the parallel approach is a random forest. Ensemble approaches can use any machine learning algorithm as base learners. However, they'll achieve greater improvements with low bias, high variance learners like decision trees. In this notebook, we try 4 different ensemble methods on a fishing data set: boosting from library Adabag, random forest, Adaboost, and XGBoost. First, the fishing data set from the UCI repository is converted from the Weka format to an R data frame, and then split into train and test sets. The data set has 11,000 rows and 30 predictors for the result target, which is a binary variable indicating fishing or not. The target column is fairly well balanced, with 56% of observations in one class and 44% in the other. Logistic regression was run as a baseline and received an accuracy of 94%. In addition, the Matthews correlation coefficient was calculated as 87%. Recall that accuracy ranges between 0 and 1, and MCC ranges between -1 and +1. The random forest algorithm was run on the same data and achieved one of the highest accuracy scores of 96% and one of the highest MCC scores of 93%. Whereas bagging uses subsets of the data, boosting uses the entire training data. Another key difference is that bagging builds learners in parallel, boosting builds them sequentially. The boosting approach learns more slowly than the bagging approach. When using decision trees as learners, the trees that are built are small, with just a few nodes. Each subsequent tree that's built is added to the function in order to update the parameters. As each new learner is built, the data is weighted according to the mispredictions of previous learners. Observations with larger errors are given larger weights so that the next learner can overcome the deficiency. This code block shows how to run the algorithm. We're running the boosting function from library Adabag. The first argument is a typical R formula, and the second is the data. The third argument here, boost equals true, indicates that a bootstrap sample of training data is used. If that's false, the entire data is used. The mFinal parameter is the number of iterations in boosting, or the number of trees. The default is 100. The coef_learn parameter here selects the algorithm that determines the alpha parameter, which is a weight for each tree in the ensemble. This code takes almost a minute to run. And notice that when we do our predictions down here, that we need to specify pred $class to extract the predictions. Our accuracy was almost 95%, and the MCC of almost 90%. Adaboost, adaptive boosting, is a variation of the boosting algorithm that trains a given number of learners one at a time. For the first iteration, the weights for training examples are equal, 1/n, where n is the number of observations. In each subsequent iteration, the weights for observations with large errors are increased, while those that are correct are decreased. As each learner is trained, its weighted error is recorded. After iterating over all the learners, these weighted errors are used to weight the learners themselves, so that more accurate learners are given higher weights. There are many Adaboost implementations in R. The one I'm going to look at is Fast Adaboost. It uses C++ code to run about 100 times faster than native R-based libraries, according to their documentation. As of today, it works only for binary classification problems, whereas the Adaboost package that we just looked at has been extended for multi-class classification. Both of those packages implement Freund and Shapiro's Adaboost M1 algorithm and Zhu's SAM algorithm. This did run very quickly, in a matter of a second or two. Our accuracy was very high, 0.96, and with an MCC of 0.93. The XGBoost extreme gradient boosting algorithm was developed by Qianqi Chen and presented in the 2016 KDD conference. The chief improvements in the algorithm result in extreme scalability, running up to 10 times faster than earlier algorithms. The R implementation of the XGBoost algorithm won the 2016 John M. Chambers Statistical Software Award. This award is well-deserved since this package runs faster than Python sklearn's version and earlier R versions. The computational part of the package is written in C++ and can take advantage of multi-threading on a single machine. One downside of running XGBoost is that the training data has to be converted into a numeric matrix and training labels converted into 0-1 encoding. So you can see here that I changed the original decoding, which was a +1, -1, into 1 and 0, and I had to convert the training data, except for the label here, into a matrix. The first argument is that training matrix that does not include the label. The second argument is the label, and we can specify our objective function and our number of rounds. The first time I ran this, I have n rounds equals 5, and it got slightly less performance than the other algorithms in this notebook. Then I bumped it up to 100, and you can see the training error go down. I was worried that it might be overfitting with that many rounds. But then when I ran the results, I saw that it got very, very good results. Really the highest accuracy of 0.9649, and also the highest MCC of 0.928, almost 0.93 there. In this notebook, we compared several different ensemble methods. Ensemble methods often use high variance learners such as decision trees as base learners. And the ensemble techniques will reduce the variance of decision trees. Bagging is especially good at reducing variance, while boosting is better at decreasing bias.